So the first part of the problem, they just want us to find the indicated partial derivatives. Partial derivatives are quite straightforward here, at least the starting part. And once you understand how they go, it becomes straightforward on how you actually have to evaluate these partial derivatives. Take, for example, the first partial derivative there. They're saying get the partial of x at the given point. So at that point. And then they are also asking us to get the second partial derivative of the function that order. So how do we obtain the partial derivative here? So a partial derivative just tells us to say that you might be dealing with a function of several variables, but approach it as if everything else was constant other than the variable that you're currently focusing on. Take, for example, here. In this expression, f of x comma y, so it's a function of two variables, and then the two variables are x and y. But when trying to get the partial derivative with respect to x, so what this implies is that treat y as a constant. So it's just like any random number, 2, 3, 4, just any real number. And then x is the variable. So we are differentiating with respect to x, meaning y here will be taken as a constant. So if y is a constant, just any random constant, how would you differentiate it? Of course, this just becomes like x to the power n. So n there becomes just any real number. So if you had to differentiate something like this, you know to say n comes down, and then here this reduces by 1 because that is just basically a constant. So in the same way, if we have to treat y as just any random constant here, we know to say this is going to multiply down, and then x to the power, then whatever to that, we're going to reduce it by 1. So basically, this becomes the partial derivative of f with respect to x. Now, they're saying we're getting the partial derivative at a specific point, at f of x at a point negative 2, 2. So at the point negative 2, 2, now it implies that at that point, x is negative 2, y is 2. So here, where there's x, would put negative 2, where there's y, would put 2. So I have a 2 here, and then we have x here, where there's x, we're putting negative 2. And then we have, that's negative 2 to the power 2 minus 1. So again, I hope you're seeing this, where there's x, and that's why where there's x, I'm putting negative 2. So be very careful with the way you are presenting that one. Like the way I've presented it here, this is actually not okay. The best way to present it is 2 here for y, and then the negative 2 for x here, and then it's the negative 2 for x that must be raised to the power y minus 1. So y minus 1 will be 2 minus 1. This is a better way of presenting it than the way I presented it there. Of course, for this particular problem, it would not change the meaning because, of course, it would still be the same negative 2 as the answer. But had the power been even or something else, it would have, I say even, it would have affected the negative. The overall answer would have been different and would have gotten it wrong. So here, of course, we'll present it this way, not this way. So I hope you've understood why this way of presenting is better. And from here, would end up having 2 negative 2. Then 2 minus 1, we know that is just going to give us a 1. So this will just be to the power 1. And finally, we have minus 4. So this is the value of this partial derivative of x at that particular point. So here, of course, we are working out this where we're finding the partial derivative with respect to x at a specific point. Okay, that is done. In the second part, they're now asking for that evaluation. So how would we do something like this? Still the same expression. Now for this one, what do you do? Since we had already obtained the partial with respect to x, so we already obtained the partial of partial f, partial x. So now we'll just go ahead and get the second partial derivative. This one, the response came out as y, x, and then y minus 1. This is what we ended up having when we got partial f, partial x. Now, to this expression, we'll now get its partial derivative, but this time with respect to y. So we get this partial derivative of this, but now with respect to y. So what happens this time? This time around, we are treating y as a variable. So don't get confused with the presence of that. What we have there is basically just the partial with respect to y this time of the solution to this. And the solution to that is this expression, y, x, y minus 1. Okay, so here what are we doing? So now here we're treating y as the variable. In other words, we're taking x as a constant. So if we're taking x as a constant, what happens? So if y is the variable, notice that now we're seeing this to say it's a product of two functions. One, it's this function, and the second part is that function there. So how do we differentiate something like that? Of course, we're going to use product rule. So you can start by keeping x to the power y minus 1, differentiate y, and the derivative of y with respect to y will be 1. So it will remain like this. Then plus, now we will keep y, and we have to differentiate this expression. Now that's where the trick is. How do we differentiate x to the power y minus 1 with respect to x? So if we're differentiating this with respect to x, not with respect to x, this is with respect to y. So if we're differentiating this with respect to y, you have to somehow view x as a constant. So as just some real number. So if x is being viewed as a constant, then the derivative here is as if you are differentiating an expression. Let's say I can even keep y still, a to the power some function f of y. To differentiate something like this, this is an exponent. To differentiate something like this, we know to say you first differentiate the power. After differentiating the power, multiply it with ln the base, whatever this is. After that, multiply it with the original function unchanged. So this is how we usually differentiate expressions of this nature. Based on that, if I wanted to differentiate this, again, I just have to view x as a constant there. So I'll differentiate y minus 1. Y as the variable, the derivative of y will be 1. The derivative of negative 1 will be 0. So the derivative of the function, the derivative of the power, will just be 1. Next, ln the base. The base here is x. So ln the base will be ln x. Then finally, multiply by the same expression without changing it. So multiply this with x to the power y minus 1. So that from here, now we can simplify that expression. So that this reduces to x to the power y minus 1 plus, this will just be, I can distribute the y. So this is now just y ln x, and then x to the power y minus 1. So this becomes the second partial derivative. So, yes, please. There, when distributing, I think you have to distribute to x to the power minus 1. This is multiplication. In multiplication, if I have 2x multiplying y, this is the same as just 2xy. There's no need for me to say I'll multiply it there. Oh, okay, I didn't see that. Yeah. Okay, so basically this is how it goes. So notice that in the problem, they wanted partial, the second partial, and then the mixed partial down here, it's partial x, partial y. The one I evaluated looks like this. You have to know to say that this is the same as this. They give you the same solution. So here I just went straight to obtaining this because I already had partial f partial x. So I just got the partial derivative of that with respect to y. But you can still start from the beginning by getting partial f partial y first. Then after getting that, get partial, the same partial, differentiate it this time with respect to x. You'll see that the answer you get will be the same as the one obtained here. So perhaps you can try that to just make sure you deepen your understanding of the concept. Okay, so I hope we are okay with that part.